As we stand on the brink of a new era in artificial intelligence, it's the creative might of generative AI, Gen AI, that heralds the most exciting advancements. Our journey through the realm of Gen AI has unveiled a landscape where AI is not just a tool for analysis, but a wellspring of creation, bridging the gap between data and imagination. Our first foray was into the fundamentals of AI, where we glimpsed its potential to not only automate, but innovate. AI serves as the canvas on which generative AI paints, providing the basic strokes that evolve into complex patterns. Here, we saw how AI's ability to interpret and interact with the world forms the foundation for its generative power. Next, we'll cover the basics of machine learning, and ML is where Gen AI begins to take shape, learning from data to predict and create. We delved into ML's basics to understand how it informs Gen AI's ability to generate new content that's both original and functional. The algorithms we explored here are the very ones that Gen AI harnesses to learn from patterns and produce novel outputs. Then we'll see introduction to neural networks. Neural networks brought us closer to understanding how Gen AI replicates the intricacies of human thought processes. These networks are the scaffolding of Gen AI's architecture, enabling it to process complex information and generate outputs that are as nuanced as they are varied. After that, with an overview of deep learning, we examined the multi-layered neural networks that empower Gen AI with its depth of knowledge. It's within these layers that Gen AI finds the capacity to create content with a level of sophistication that blurs the lines between artificial and human. Then we'll understand large language models, LLMs, which presented a world where language is not just understood, but also woven anew. Gen AI's prowess in language was showcased through models like GPT and BERT, which generate text that resonates with human expressiveness and contextual depth. Then, venturing into generative AI concepts, we embraced AI's role as an artist and an inventor. We discovered how Gen AI is not constrained by what exists, but is inspired to create what could be, from art to music to hypothetical scenarios, expanding the horizons of creativity. In discussing generative models in AI, we unraveled the mechanisms of GANs and VAEs, the virtuosos of the generative world. These models are the artisans, meticulously crafting and refining output until it stands indistinguishable from that created by human hands. Then we'll cover the mathematical foundations of generative AI that revealed the robust framework underpinning Gen AI's capabilities. From probability to complex statistical models, we explored the quantitative bedrock that allows Gen AI to simulate the richness and diversity of the real world in its creations. Then we'll recall all the concepts which we covered so far at the end. Generative AI stands as a testament to human ingenuity, embodying our innate drive to create and explore. Throughout this course, we've seen how Gen AI not only replicates but also enriches our reality, crafting content that pushes the boundaries of what machines are thought capable of. As we conclude, let's carry forward the knowledge that Gen AI is more than a technological marvel. It's a catalyst for innovation, a partner in creativity, and a beacon for the future of artificial intelligence. Let's discuss the fundamentals of artificial intelligence, a field that's not just revolutionizing technology, but also the way we live, work, and interact with the world. AI is no longer just a futuristic concept. It's here, and it's impacting everything from our smartphones to global industries. Let's start by breaking down what AI really is. Imagine having a digital colleague that can not only perform tasks, but also think and learn like us. This is where AI comes into play. AI isn't just programming, it's about creating intelligent behavior in machines. It's a blend of sophisticated algorithms and computational power, designed to mimic human cognition. In its essence, AI is a marvel of computer science. It involves writing algorithms that empower machines to undertake tasks that would typically require human intelligence. These aren't just simple rule-based tasks, but complex activities needing understanding and decision-making. The beauty of AI lies in its ability to adapt and learn from experience, much like how we humans do. AI's capabilities are extensive. It can interpret vast amounts of data, recognize intricate patterns, and even make decisions based on its analysis. Think about a simple online search. When you type in a query, AI algorithms work in the background to understand your request, sift through countless data points, and present you with the most relevant results. This process exemplifies AI's capability to process and interpret data at an extraordinary scale and speed. Another cornerstone of AI is pattern recognition. This is where AI truly shines. From identifying faces in photos to predicting consumer behavior based on past purchases, AI can discern patterns in data that are often too complex or subtle for human analysis. This ability is paramount in fields like medical diagnostics, where AI systems can detect patterns in X-rays or MRI scans that might elude even seasoned professionals. AI's decision-making process is another aspect that sets it apart. This isn't about following a predetermined set of instructions. AI decision-making involves analyzing data, weighing different outcomes, and choosing the best course of action. This facet of AI is revolutionizing industries. In finance, for instance, AI systems analyze market trends, predict stock performance, and can even autonomously execute trades, all based on their data-driven decisions. AI's reasoning capabilities are equally fascinating. It's not just about crunching numbers or processing information. AI can reason out solutions to problems, sometimes in ways that even surpass human capabilities. Take the example of AI in chess or Go. These AI systems don't just calculate moves, they strategize and reason, often outmaneuvering world champions. As we delve deeper into this, we'll explore the intricacies of AI algorithms, how they're designed to mimic human intelligence, and the ways they're transforming our world. We'll look at various AI applications that have become integral parts of our daily lives and understand the underlying principles that make these technologies possible. But how did we get here? AI's journey began way back in the 1950s. It's a story of ambitious dreams, significant breakthroughs, and yes, even a few setbacks. We've seen AI's capabilities grow from simple chess-playing programs to today's smart assistants capable of understanding and responding to natural language. This evolution was propelled by two major forces: the explosion of data and the advancement of neural networks, especially deep learning. These factors have enabled AI to analyze and learn from vast amounts of information, leading to the sophisticated systems we see today. Now let's talk about the types of AI. AI can be broadly categorized into narrow AI and general AI. Narrow AI, which is what we mostly encounter today, is designed for specific tasks. Whether it's recommending a song on Spotify or providing driving directions, these systems excel in their designated functions but don't possess broader intelligence. On the other hand, general AI, a goal yet to be achieved, aims to replicate human intelligence in a comprehensive manner, capable of performing a wide range of tasks with cognitive abilities akin to humans. Artificial intelligence has transitioned from a futuristic concept to an integral part of our daily lives. Its applications range from the overtly obvious to the subtly profound, reshaping the way we interact with technology and the world around us. Let's start by looking at the most visible and interactive aspects of AI in our daily lives. When you use a digital assistant like Siri or Alexa, you're interacting with AI. These systems understand your voice commands, process your requests, and learn from your preferences to provide personalized responses. They're a perfect blend of natural language processing, a branch of AI that deals with the interaction between computers and human languages, and machine learning, enabling these assistants to learn from your habits and preferences. But AI's presence goes beyond just digital assistants. It's in our homes, embedded in smart appliances like thermostats, that learn our preferences for temperature and adjust accordingly. Or consider the recommendation systems used by streaming services like Netflix or Spotify. They analyze your viewing or listening history, process vast amounts of data on content, and use sophisticated algorithms to recommend shows or music tailored to your tastes. Now let's delve into user interface technologies. Ever noticed how your smartphone keyboard predicts the next word you're about to type? That's AI at work, using predictive text algorithms based on your typing history and common language patterns. This seemingly simple feature exemplifies AI's capability to enhance user experience by anticipating user needs. Moving beyond these everyday interactions, AI plays significant yet less visible roles in various sectors. In finance, for instance, AI is revolutionizing the way we approach money management and investment. AI algorithms analyze market trends, predict stock performances, and even autonomously execute trades. They can process more data at a faster rate than any human could, enabling more informed and timely investment decisions. In logistics, AI is optimizing supply chain management. It's used to predict demand, manage inventory, and optimize delivery routes. By analyzing historical data and current market trends, AI helps companies anticipate changes in demand, reducing waste and improving efficiency. In the realm of cybersecurity, AI is a formidable tool. It monitors network traffic for unusual patterns, identifies potential threats, and responds to security incidents. AI's ability to rapidly analyze vast amounts of data and identify anomalies makes it an essential component in modern cybersecurity strategies. In the next part, we'll delve into the transformative impact AI is having on industries and the workplace. We'll discuss how AI is not just automating tasks, but also augmenting human capabilities, leading to more efficient and effective work processes. This exploration will provide a comprehensive understanding of AI's vast potential and its profound implications for the future of work and industry. Let's delve into how AI is revolutionizing business operations. The most apparent impact is in manufacturing, where AI-driven automation is creating a new era of production. Robots in factories aren't a new concept, but when infused with AI, they can make intelligent decisions, adapt to different tasks, and work more efficiently alongside human workers. These smart robots can detect and correct errors, predict maintenance needs, and optimize production processes, leading to significant increases in efficiency and reduction in costs. But AI's influence extends far beyond the factory floor. In the realm of strategic business analysis, AI algorithms are capable of sifting through massive datasets to extract actionable insights. These insights enable companies to make informed decisions about market trends, customer preferences, and potential investment opportunities. By harnessing the predictive power of AI, businesses can anticipate market shifts, tailor products to consumer needs, and even preemptively address potential operational challenges. AI is also transforming customer service. Chatbots powered by AI are providing instant customer support, handling inquiries, and solving problems around the clock. They're capable of learning from each interaction, becoming more efficient and effective over time. This not only improves customer experience, but also frees up human agents to handle more complex issues, enhancing overall service quality. In the healthcare sector, AI's impact is profound and multifaceted. One of the most critical applications is in diagnostics. AI algorithms are being trained to read and interpret medical images, such as X-rays and MRI scans, with a level of precision that matches or even surpasses human radiologists. These algorithms can detect subtle patterns and anomalies that might be missed by the human eye, leading to earlier and more accurate diagnoses. But AI's role in healthcare goes beyond diagnostics. In the field of drug discovery and development, AI is dramatically accelerating the process of creating new medications. By analyzing vast data sets of molecular structures and biological interactions, AI can predict which compounds are most likely to succeed as effective drugs, thereby reducing the time and cost of bringing new treatments to market. Personalized medicine is another area where AI is making a significant impact. By analyzing a patient's genetic makeup, lifestyle, and environmental factors, AI can help tailor treatment plans to individual needs. This approach increases the effectiveness of treatments and minimizes side effects, leading to better patient outcomes. Looking ahead, the future of AI is incredibly promising. We're at the brink of a new era where AI could help us tackle some of the world's most pressing challenges, from climate change to sustainable development. As we continue to innovate and integrate AI into various aspects of society, it's essential that we also prepare ourselves, through education, policymaking, and public awareness, for a future where AI plays an even more integral role. As we continue our journey into the world of AI, having explored its transformative impact across various industries, it's essential to pivot and look at the other side of the coin, the limitations and challenges of current AI systems. Understanding these limitations is crucial to appreciate AI's potential realistically and to navigate its future responsibly. AI, as revolutionary as it is, isn't without its limitations. One of the primary constraints is its dependency on data quality. AI systems learn and make decisions based on the data they're fed. If this data is biased, incomplete, or flawed, the AI's outputs will be too. This is akin to the saying, garbage in, garbage out. For instance, if an AI system is trained on medical data that lacks diversity, it may not perform accurately across different demographics. Another significant limitation is AI's struggle with context recognition. AI systems, particularly those based on machine learning algorithms, excel at identifying patterns and making predictions. However, they often lack the ability to understand context in the way humans do naturally. This becomes evident in tasks involving complex language understanding or situations where context changes rapidly. For example, AI may excel at language translation but struggle to grasp the nuances and cultural contexts of the languages it translates. Then, there are ethical considerations. AI raises numerous ethical questions, from privacy concerns in data handling to the potential for reinforcing societal biases. AI systems are only as ethical as the data and objectives they are given. Without careful consideration and intentional design, AI can inadvertently perpetuate existing biases, as seen in some facial recognition technologies that have demonstrated bias against certain demographic groups. Then, we have another limitation, which is human oversight in AI implementation. AI, no matter how advanced, should not operate in a vacuum. Human intervention is essential, not only in the design and training phases, but also in the application and governance of AI systems. Human oversight ensures that AI operates within ethical boundaries and with a level of understanding and empathy that AI alone cannot achieve. For instance, in healthcare, while AI can assist in diagnosing diseases, human doctors are crucial for interpreting these diagnoses in the context of a patient's overall health and personal circumstances. Similarly, in judicial systems, AI might help analyze legal documents quickly, but human judgment is vital to ensure justice is served with fairness and empathy. As we've seen, AI's versatility and impact are profound. Now we turn our focus to machine learning, ML, a crucial component that propels AI's capabilities to new heights. Let's dive into the intricacies of ML and uncover its foundational concepts and applications. Transitioning from our discussion on the limitations and challenges of AI, let's delve deeper into one of its most dynamic branches, machine learning, ML. Understanding ML is key to appreciating how AI systems learn, adapt, and make decisions. At its core, machine learning is a subset of AI focused on building systems that learn from data. Unlike traditional software programs that follow explicit instructions to perform a task, ML algorithms use data to train themselves and improve their performance over time. This process is akin to how we humans learn from experience. Imagine teaching a child to recognize different types of fruits. You show them various fruits and name them until the child learns to identify and categorize them independently. Machine learning works in a similar way. You feed an algorithm data, in this case, pictures of fruits and their names, and it learns to recognize and categorize new data, fruits, based on that training. Machine learning is essentially about achieving AI through experience. It's about creating algorithms that don't just perform tasks, but also learn and improve as they encounter more data. This ability to improve is what makes ML a cornerstone in the AI field. Whether it's speech recognition in virtual assistants or recommendation engines on e-commerce sites, ML is what enables these systems to get better and more personalized over time. One of the primary functions of ML is to analyze historical data to find patterns and insights. This capability is invaluable across many fields. In finance, ML algorithms analyze market trends to predict stock movements. In healthcare, they sift through patient data to identify potential health risks or disease markers. These algorithms can sift through vast amounts of data, much more than any human could process in a lifetime, and find correlations and patterns that might not be immediately apparent. This data-driven insight generation is what makes ML so powerful and versatile. A defining feature of ML is its ability to adjust and improve with new data. As more data is fed into an ML system, it can refine its algorithms, becoming more accurate and efficient over time. This aspect of continuous learning is what differentiates ML from static software programs. For instance, consider a spam filter in your email. Initially, it might only block emails that meet certain obvious criteria of spam. But as it processes your interactions, which emails you mark as spam or not, it gets better at filtering out unwanted emails, adapting to new spamming tactics. ML involves converting data inputs, like images, text, or numbers, into meaningful outputs or decisions. This process is central to ML's utility. For instance, in image recognition, ML algorithms analyze pixel data to identify and categorize objects in the image. In predictive maintenance, ML algorithms process sensor data from machines to predict when they might fail. The accuracy of ML algorithms generally increases as they gain more data and experience. This increasing accuracy is crucial for applications where precision is paramount. In medical diagnostics, for instance, the more patient data an ML algorithm processes, the better it becomes at diagnosing diseases accurately. Lastly, ML enables the automation of decision-making processes in various applications. This ability is transforming industries by allowing for efficient and rapid decision-making without human intervention. From automated trading systems in finance to autonomous driving in vehicles, ML algorithms are making complex decisions, often in real time, based on the data they process. Exploring the types of ML, we begin with supervised learning, where algorithms are trained using labeled data. This method is like a guided learning process, with clear indicators of right and wrong. Common examples include email classification and predictive analytics. In contrast, unsupervised learning deals with unlabeled data, allowing algorithms to identify inherent patterns and relationships. This type is crucial in uncovering hidden insights, such as customer segmentation in marketing. We also encounter semi-supervised and reinforcement learning, which offer unique approaches to training models, the former using a mix of labeled and unlabeled data, and the latter learning through trial and error. Classification algorithms are a staple in ML. They're used to categorize data into predefined classes or groups. Think of it like sorting different fruits into baskets based on their types. One classic example is decision trees. Imagine a flowchart-like structure where each node represents a decision based on a certain attribute of the data. For instance, in email filtering, a decision tree might classify emails as spam or not spam based on keywords, sender, or other characteristics. Decision trees are popular due to their simplicity and interpretability. You can easily trace back the path and understand why a particular decision was made. Another powerful classification algorithm is support vector machines, SVM. SVMs are particularly adept at handling high-dimensional data. They work by finding the best boundary, or hyperplane, that separates data points of different classes. The beauty of SVM lies in its ability to manage complex classification tasks, such as image classification, where it distinguishes between different objects within an image. While classification deals with discrete outputs, regression algorithms predict continuous outcomes. It's like predicting the temperature for the next week based on past data. A fundamental regression algorithm is linear regression. Here, a straight line is fitted through the data points that best represents the relationship between the input variables and the outcome. This algorithm is widely used in forecasting and predicting trends. For example, in real estate, it can predict house prices based on features like size, location, and age. Then there's polynomial regression, a more flexible variant of linear regression. It's used when the data points form a nonlinear relationship. By incorporating polynomial terms, like squares or cubes of the input variables, it can model more complex relationships, like the growth pattern of a certain crop under varying environmental conditions. After this, clustering algorithms are also a part of ML algorithms, which are used to group similar data points together. Unlike classification, where groups are predefined, clustering identifies these groupings inherently present in the data. It's like organizing a library of books into genres without knowing the genres in advance. K-means is a popular clustering algorithm. It partitions data into K-distinct clusters based on their features. The algorithm assigns each data point to the nearest cluster while keeping the clusters as distinct as possible. It's widely used in market segmentation, where customers are grouped based on purchasing behavior, interests, or demographics. Another clustering technique is hierarchical clustering. This algorithm builds a hierarchy of clusters, creating a tree-like structure of data. It's particularly useful in biological applications, like classifying species based on genetic characteristics. These algorithms, classification, regression, and clustering, form the bedrock of machine learning. Each has its unique way of learning from data and making predictions or categorizations. As we progress, we will delve deeper into how these algorithms are applied in real-world scenarios, transforming industries and everyday life. In the world of data, more isn't always better. Sometimes data sets have so many variables or dimensions that it becomes challenging to process them efficiently, a phenomenon known as the curse of dimensionality. This is where dimensionality reduction techniques come into play. Imagine you're a chef trying to focus on the essential ingredients for a dish while ignoring the less impactful ones. Dimensionality reduction does something similar. It reduces the number of input variables in a data set while retaining as much of the important information as possible. A prime example of this technique is principal component analysis, PCA. PCA simplifies data by transforming the original variables into a new set of variables, the principal components. These components are ordered so that the first few retain most of the variation present in all of the original variables. In real-world applications, PCA is used in fields like finance for risk assessment models and in bioinformatics for genetic data analysis. Another fascinating tool is T-Distributed Stochastic Neighbor Embedding, TSNE, which excels in visualizing high-dimensional data. TSNE maps complex datasets into 2 or 3 dimensions, making it easier to identify patterns and clusters visually. It's particularly useful in machine learning projects where understanding the structure of data is crucial. Ensemble methods are like the wisdom of crowds in machine learning. Instead of relying on a single learning algorithm, these methods combine multiple algorithms to improve prediction accuracy. The idea is that by combining the strengths of various models, we can compensate for the weaknesses of individual ones. Take random forests, for instance. It's an ensemble method that combines multiple decision trees to produce a more robust and accurate prediction model. Each tree in a random forest is trained on a subset of the data and makes its own predictions. The final output is determined by majority voting or averaging the predictions of all trees. This method is widely used in classification and regression tasks, from credit scoring to medical diagnosis. Another powerful ensemble technique is gradient boosting. This method builds models in a stage-wise fashion, with each new model being trained to correct the errors made by the previous ones. It's particularly effective in situations where precision is key, like in competitive data science or complex risk modeling. Now, let's turn to the cutting edge of ML, which is neural networks and deep learning. These algorithms are inspired by the structure and function of the human brain. They consist of layers of interconnected nodes, or neurons, that process data in complex ways. Convolutional neural networks, CNNs, are a type of deep neural network specially designed for processing structured grid data, such as images. CNNs use a mathematical operation called convolution to process data in small chunks, capturing the spatial relationships in the data. This makes them exceptionally good at tasks like image recognition and video analysis. Another significant type is recurrent neural networks, RNNs, known for their ability to handle sequential data, like time series or natural language. RNNs have connections that form loops, allowing information from previous steps to persist, which is crucial in understanding context in sequences. They're instrumental in applications like language translation and speech recognition. Here, we've seen how ML is not just a single approach, but a spectrum of techniques, each with its strengths and applications. From simplifying data through dimensionality reduction to making robust predictions with ensemble methods and mimicking human thought processes through neural networks, ML's versatility is what makes it such a powerful tool in AI. Building on our exploration of machine learning algorithms, we now turn to a fundamental component in the ML landscape: neural networks. These networks, inspired by the human brain, have revolutionized how we approach complex problems in ML. Neural networks are like the brain's digital counterpart. They're composed of layers of interconnected nodes, or neurons, each designed to mimic the function of neurons in the human brain. These networks are adept at identifying patterns in complex data, a task that is challenging for traditional algorithms. Imagine you're trying to recognize a face in a crowd. Your brain processes various features like the shape of the eyes, the color of the hair, and the contour of the face. Neural networks do something similar. They analyze different features of data, be it pixels in an image or sound frequencies in audio, to identify patterns. These networks are structured in layers: the input layer, one or more hidden layers, and the output layer. The input layer receives the raw data. This data is then passed through the hidden layers, where the actual processing happens through a complex web of nodes. Finally, the output layer produces the result, be it a classification label or a predicted value. The magic of neural networks lies in these hidden layers. The more layers, or the deeper the network, the more complex the patterns it can recognize. This is where deep learning comes into play, but more on that later. Next, we'll discuss an integral part of neural networks, which is the activation function. These functions decide whether a neuron should be activated, meaning whether it should pass its information to the next layer. It's like a filter that decides what information is important enough to move forward. Common activation functions include the rectified linear unit, ReLU, sigmoid, and ton. Each has its own way of deciding what information gets through. For example, ReLU is simple yet effective. It passes positive values as is, but blocks negative values. This simplicity allows networks to train faster and handle more complex data. Now, one of the key processes in training neural networks is backpropagation. Here's where the network learns from its mistakes. When a neural network makes an error, say misidentifying a picture of a cat as a dog, backpropagation adjusts the weights of the network. This adjustment is done based on the error rate, improving the network's accuracy over time. Deep learning is essentially neural networks with multiple hidden layers. These additional layers enable the network to learn and represent data with a level of complexity and abstraction that wasn't possible before. Deep learning has led to significant breakthroughs in areas like computer vision and natural language processing. Next, let's discuss the applications of neural networks, which are vast and varied. In image recognition, they analyze pixel data to identify and categorize objects within images. In speech recognition, they process audio data to understand and interpret human speech. And in natural language processing, they're used to comprehend and generate human-like text, transforming how machines interact with human language. A critical aspect of ML is evaluating model performance. Accuracy is the measure of a model's overall correctness, while precision assesses the relevance of its predictions. Recall evaluates the model's ability to identify all relevant instances, and the F1 score provides a balance between precision and recall. These metrics are fundamental in assessing and refining ML models, ensuring their reliability and applicability in various scenarios. To understand the real-world impact of ML, consider its diverse applications. One of the most user-friendly applications of ML is in personalization algorithms. These algorithms power platforms like Netflix and Spotify, tailoring content to individual preferences. By analyzing your past viewing or listening history, ML algorithms predict what you might like next. They constantly learn from your interactions, refining their recommendations to become more accurate over time. It's like having a personal curator who knows your taste better than you do. In various industries, ML's predictive analytics is a game changer. It's about forecasting future trends and behaviors by analyzing current and historical data. Retail companies use predictive analytics to forecast sales trends and manage inventory efficiently. In finance, these algorithms predict market trends, helping investors make informed decisions. Essentially, predictive analytics turn data into foresight, enabling proactive rather than reactive strategies. One of the most exciting applications of ML is in autonomous systems, particularly self-driving cars and automated drones. These systems rely on ML algorithms to interpret sensor data, make decisions, and navigate their environment safely. In self-driving cars, ML algorithms process inputs from cameras, radar, and LiDAR to identify obstacles, interpret traffic signs, and decide the best course of action, all in real time. Similarly, drones use ML for various purposes, from aerial photography to surveying and inspecting infrastructure. ML is revolutionizing healthcare with its advanced applications. From early disease detection to developing personalized treatment plans, ML algorithms are enhancing the precision and effectiveness of healthcare services. By analyzing patient data, medical images, and genetic information, ML algorithms can identify disease markers earlier than traditional methods, enabling timely interventions. They also assist in creating treatment plans tailored to individual patients' genetic profiles, maximizing treatment effectiveness while minimizing side effects. Another area where ML shines is natural language processing, NLP. This technology enhances language translation services and virtual assistants. NLP algorithms understand, interpret, and generate human language in a way that's natural and useful. They're the reason virtual assistants can understand your queries and respond in a conversational manner. In language translation, NLP algorithms are not just translating words, they're capturing nuances, idioms, and cultural contexts to provide more accurate and understandable translations. Lastly, in the finance and banking sector, ML plays a crucial role in fraud detection. ML algorithms analyze transaction patterns to identify unusual behavior that may indicate fraudulent activities. They learn from historical fraud data, becoming more adept at spotting anomalies. This capability is vital for protecting consumers and financial institutions from increasingly sophisticated fraud schemes. Despite its transformative potential, ML faces several challenges. Let's unpack these challenges to better grasp the complexities of working with ML. First is data quality issues. The foundation of any ML model is data. But what happens when this foundation is shaky? Poor or biased data can lead to models that are inaccurate and potentially misleading. Imagine training a facial recognition system with data that lacks diversity. The model might perform well with faces it was trained on, but fail miserably with others. This issue of biased data is a significant hurdle and can lead to models that inadvertently perpetuate societal biases. Next is quantity of training data, which is another challenge. ML models, especially those based on deep learning, are data-hungry beasts. They require vast amounts of data to learn effectively. This requirement can be a significant barrier, particularly in fields where data is scarce, sensitive, or expensive to acquire. For instance, in medical research, getting enough data for rare diseases can be challenging, limiting the ability to develop robust diagnostic tools. As we delve into more sophisticated ML models, we encounter the challenge of complexity. Complex models, like deep neural networks, require significant computational resources. Training these models can be resource-intensive, requiring powerful hardware and substantial electricity. Moreover, the complexity of these models demands a high level of expertise, which can be a limiting factor, especially in smaller organizations or for individual researchers. One of the most debated topics in ML is model interpretability. How does a model arrive at a particular decision? This question is crucial, especially in high-stakes domains like healthcare or finance. For example, if a model denies a loan application or diagnoses a disease, stakeholders need to understand why. However, as models become more complex, this interpretability often decreases, leading to what is sometimes called black box models. Ethical considerations and bias in ML models are hot-button issues. Ensuring that ML models are fair and do not perpetuate or amplify biases is a significant challenge. This concern extends beyond just the data. It encompasses the entire model development process, from the initial design to its final deployment. It's about asking not just what a model can do, but whether it should do it. Finally, the rapid pace of evolution in ML technology presents its own set of challenges. Keeping up with the latest developments, tools, and techniques requires continuous learning and adaptation. For professionals in the field, this means a commitment to lifelong learning. For organizations, it means staying agile and adaptable, ready to incorporate new advancements into their workflows. Building on our understanding of machine learning from the last slides, we now venture into the specialized realms of neural networks and deep learning. These are not just cornerstones of advanced AI applications, but are also reshaping our approach to data analysis and interpretation. We now venture into one of the most intriguing and influential areas of AI, that is neural network. These networks are not just algorithms. They are an attempt to replicate the workings of the human brain to process and interpret complex data. Imagine creating a machine that thinks and processes information like the human brain. That's the foundational idea behind neural networks. These networks are designed to recognize patterns and interpret sensory data, much like our brain does. They are a series of algorithms that mimic the operations of a vast network of neurons in a human brain. The structure of these networks is what makes them unique. They consist of layers of interconnected nodes, often referred to as neurons. Each of these nodes is like a miniature data processing unit, working together in a structured and hierarchical manner. This structure allows neural networks to handle and interpret complex, high-dimensional data like images, sound, and text. A typical neural network includes several layers: an input layer, one or more hidden layers, and an output layer. The input layer receives the initial data, much like our senses pick up stimuli. The hidden layers, which form the core of the network, process this data. Finally, the output layer produces the result, the network's interpretation or prediction. The magic happens in these hidden layers. Each layer contains multiple nodes or neurons, and these are where the actual processing occurs. The nodes in these layers are interconnected through weights, which are essentially the strength or intensity of the connection between nodes. As data passes through these layers, each neuron processes it based on these weighted connections. Now let's talk about the neurons themselves. Each neuron in a neural network processes the input data it receives, applies what's known as an activation function, and then passes its output to the next layer. The activation function is crucial. It determines whether or not a neuron should be activated. You can think of it as a filter that decides how much of the input should be passed on. Common activation functions include ReLU, rectified linear unit, and the sigmoid function. ReLU, for instance, allows only positive values to pass through, effectively enabling the network to handle nonlinear data, a crucial capability for dealing with complex, real-world data. In essence, neural networks, through their layers and neurons, are able to transform raw, unstructured data into meaningful outputs. This capability is what powers many of the AI applications we see today, from voice recognition systems to sophisticated image analysis tools. Let's discuss learning in neural networks. As our brains learn from experience, neural networks learn by adjusting weights, parameters that determine how much influence one node in the network has over another. These adjustments are made based on the error rate of the network's predictions during training. Think of it like teaching a child to ride a bike. Each attempt helps the child adjust their balance and pedaling, getting better over time. In neural networks, this process of learning and adjusting is done through algorithms such as backpropagation and gradient descent. Backpropagation helps the network understand the error in its predictions, and gradient descent is a method to minimize this error by iteratively adjusting the weights. Neural networks come in various forms, each suited for different types of tasks. Convolutional neural networks, CNNs, are widely used for image processing. They excel at recognizing patterns in images like identifying objects or faces. This is why they're at the heart of facial recognition technologies and medical imaging analysis. Another type is recurrent neural networks, RNNs, which are designed for sequential data. They are particularly useful in processing time series data or language. This capability makes RNNs ideal for applications like speech recognition or language translation, where understanding the sequence and context of words is crucial. Now, move to the applications. The applications of neural networks are vast and diverse. In image and speech recognition, they have enabled machines to interpret and understand visual and auditory inputs almost like humans. Your phone's ability to recognize your voice commands and social media platforms' capability to automatically tag your friends in photos are powered by these neural networks. In natural language processing, neural networks help machines understand, interpret, and respond to human language in a way that is both meaningful and contextually relevant. This technology is behind chatbots that provide customer service or AI assistants like Siri and Alexa, and let's not forget about autonomous vehicles. These vehicles use neural networks to make sense of their surroundings, process sensory data, and make decisions in real time, paving the way for safer and more efficient transport systems. Now, let's discuss deep learning concepts in brief. Later, we dive into this concept more. Deep learning takes neural networks to the next level. We're talking about networks that are deep with many layers, enabling them to learn and make decisions from incredibly complex data sets. Deep neural networks learn different features at each layer. The first layer might recognize edges in an image, while deeper layers might identify more complex features like shapes or specific objects. Deep learning excels when it has access to large amounts of data. The more data these models are fed, the more accurate they become, making them incredibly powerful tools for tasks like image and voice recognition. While deep learning is a game changer in AI, it comes with its own set of challenges. One of the primary hurdles is the need for substantial computational power and large data sets. Deep learning models, especially those involving neural networks, require immense processing capabilities, often necessitating specialized hardware like GPUs or TPUs. This can make DL resource-intensive and sometimes inaccessible for smaller organizations or projects. Another challenge with deep learning models is their nature of being black boxes. What this means is it can be difficult to interpret how these models make decisions. Unlike simpler algorithms where the decision-making process is more transparent, DL models, due to their complexity and layers of computations, often don't offer a clear pathway of their internal workings. This opacity can be a significant issue, especially in sectors where understanding the rationale behind decisions is crucial, like in healthcare or finance. Then comes training DL models that involve feeding them large data sets, through which they learn to recognize patterns and make decisions. This training process is at the heart of deep learning's capability. For instance, in image recognition, a model is trained with thousands, sometimes millions of images, so it learns to identify and categorize various objects in images. However, training DL models is not just data-intensive, but also computationally expensive. It requires sophisticated optimization techniques to adjust the model's parameters effectively. The models go through an iterative process where they continuously learn and improve their accuracy. This requires a delicate balance of resources, time, and technical expertise. Despite these challenges, the practical applications of deep learning are both impressive and impactful. Take language translation services, for example. DL models have revolutionized our ability to translate languages in real time, breaking down communication barriers and facilitating global interactions. In healthcare, deep learning is making strides in medical diagnosis. Models trained on medical imaging data can assist doctors in diagnosing diseases from scans, sometimes with higher accuracy or quicker than human analysis. This is a boon, particularly in analyzing complex images like MRIs or CT scans. Another area where DL shines is in recommendation systems. The advanced algorithms can predict user preferences with remarkable accuracy, enhancing user experience in streaming services, e-commerce, and content platforms. Now we'll understand convolutional neural networks. Convolutional neural networks are a breed of deep neural networks specifically designed to process data that comes in a grid-like format, such as images. The key to their success lies in their ability to recognize patterns within these grids, making them incredibly efficient for image processing tasks. The magic of CNNs begins with their unique structure, which allows them to automatically and adaptively learn spatial hierarchies of features. What does this mean? Essentially, CNNs can learn to identify patterns such as edges and textures in early layers and more complex features like objects and faces in deeper layers. This hierarchical approach to learning makes CNNs particularly adept at understanding the intricacies of visual data. Now we move to the architecture of a CNN. which is a fascinating combination of different types of layers, each contributing to the network's ability to discern and interpret visual information. Typically, a CNN includes convolutional layers, pooling layers, and fully connected layers. Convolutional layers are the core building blocks of a CNN. They apply a convolution operation to the input, effectively passing a filter or kernel over the image to create a feature map. This process helps the network focus on small regions of the input, allowing it to pick up on local patterns like edges and textures. Pooling layers. Following the convolutional layers, pooling layers are used to reduce the spatial dimensions, width and height, of the input volume. They help in reducing the number of parameters, which in turn controls overfitting. Pooling layers typically perform operations like max pooling, which takes the maximum value in a certain window, or average pooling. Towards the end of the network, fully connected layers are used. These layers take the high-level features learned by the convolutional and pooling layers and use them for classifying the input image into various categories. Let's discuss more about the pooling layers, which play a crucial role. Think of them as a tool for streamlining the information the network processes. Essentially, pooling layers reduces the spatial size of the representations in the network. This means less computational burden and fewer parameters, making the network more efficient. There are a couple of common pooling operations. Max pooling, for instance, takes the largest element from the region of the feature map covered by the filter. Imagine scanning a photo and picking out the brightest pixel in each small square. That's max pooling at a basic level. Then there's average pooling, which, as the name suggests, takes the average of the elements in that region. Both methods help in reducing the computational load and in making the network less sensitive to the exact location of features in the input. One of the fascinating aspects of CNNs is how they learn to identify and recognize features. In the initial layers of a CNN, the network learns to identify basic features like edges and corners. As we move deeper into the network, it starts recognizing more complex features, shapes, textures, and eventually, entire objects. This layered learning approach is somewhat similar to how we learn to recognize objects as we grow. First, we discern basic shapes and colors, and then we start putting these together to recognize more complex objects. In CNNs, each layer builds on the previous one, refining the network's understanding and recognition ability. Now, the applications of CNNs are vast and continue to grow. In image and video recognition, they're used to identify objects, people, scenes, and actions. Think about how Facebook automatically tags photos with your friends' names. That's a CNN working behind the scenes. In image classification, CNNs have become invaluable. They can classify images into categories, which is essential in everything from organizing digital photo libraries to assisting in autonomous vehicle navigation. CNNs have also made significant strides in medical image analysis. They're being used to detect diseases from medical imagery, such as identifying tumors in MRI scans or spotting abnormalities in X-rays with a level of precision that rivals human experts. And then there's facial recognition, a field where CNNs have really shone. Whether it's unlocking your smartphone with your face or enhancing security systems, CNNs have brought a high level of accuracy and efficiency to facial recognition technology. Now let's discuss recurrent neural networks. RNNs are all about sequential data. They're uniquely designed to handle data where order and sequence matter, like language or time series. The loop structure in RNNs allows them to keep information from previous inputs, which is crucial for tasks where past information affects future outputs. It's like having a memory component within the network. However, RNNs have their limitations. They often struggle with long-term dependencies, which is where advanced versions like LSTMs and GRUs come into play. Now, we will discuss LSTM. Long short-term memory networks and gated recurrent units are specially designed to remember information over longer sequences. They use mechanisms like gates to control the flow of information, addressing the traditional limitations of RNNs. After this, we have the applications of RNNs, which are diverse and impactful. They've revolutionized fields such as natural language processing, speech recognition, and even time series analysis. In language translation services, RNNs have enabled us to break language barriers, allowing for real-time translation between languages. In the financial sector, RNNs are used for predicting stock market trends and analyzing financial data over time, offering insights that were previously unattainable. The healthcare industry benefits from RNNs in patient monitoring systems, where continuous data like heart rates are analyzed for predictive healthcare and anomaly detection. Lastly, we explored the introduction to neural networks. Now we're diving even deeper into the exciting world of artificial intelligence with a specific focus on deep learning. Deep learning, at its core, is a subset of machine learning. It's like the powerhouse of AI, allowing machines to mimic human-like decision-making processes. But what sets it apart? Well, it's all about the neural networks. Neural networks. These are not exactly biological neurons, but rather artificial neurons arranged in layers. Imagine them as the building blocks of deep learning. These interconnected neurons process and learn from data. The depth in deep learning comes from the multiple layers, which enable complex learning. Now let's move on to the core concepts. Now, let's discuss neural networks. As we mentioned, they are the backbone of deep learning. These networks comprise layers of artificial neurons that work together to process data. The deeper the network, the more intricate patterns it can recognize. Now, what about training the data? Deep learning models are data-hungry monsters. To improve their accuracy and predictive power, they need large datasets for training. It's like learning from thousands of examples to make better predictions. Now let's imagine learning from your mistakes. That's precisely what backpropagation is about. It's the process where neural networks adjust their internal parameters to minimize errors. In simple terms, it's learning from past experiences. Lastly, we have activation functions. These are the decision makers within the neural network. They introduce nonlinearity into the model, allowing it to map complex relationships between inputs and outputs. Without activation functions, we'd have linear models, and that wouldn't get us very far in the world of deep learning. Deep learning systems offer some unique and powerful features that set them apart in the AI landscape. One of the most exciting aspects of deep learning is its ability to automatically extract relevant features from raw data. It's like having a super smart detective that can spot important clues in a pile of evidence. Next is scalability. Deep learning is highly scalable. It can handle massive datasets and complex tasks. So, whether you're working with thousands of images or processing tons of text data, deep learning has your back. Now, think of transfer learning as a time-saving hack. Deep learning models can be pre-trained on one task and then fine-tuned for another. It's like having a head start. For instance, a model trained to recognize animals can be fine-tuned to identify specific breeds of dogs. Next, deep learning models are known for their impressive accuracy. In many applications, they achieve state-of-the-art results. That's why they're so popular in tasks like image recognition and natural language processing. Now that we've got a grasp of the core concepts and features, it's crucial to understand why deep learning matters. Deep learning is the driving force behind some incredible technologies. It powers image and speech recognition, making your smartphone's camera smarter. It's behind the magic of virtual assistants like Siri and Alexa, and it even helps autonomous vehicles navigate and make decisions. Deep learning has unleashed innovation across various fields. In healthcare, it aids in disease diagnosis. In finance, it improves fraud detection. In entertainment, it personalizes recommendations. The possibilities are limitless. As we look ahead, Deep learning is positioned to be a cornerstone of the future job market. Understanding it today can open doors to exciting career opportunities in AI and machine learning. To make all of this theory more tangible, let's dive into some real-world examples of how deep learning is shaping the world around us. Deep learning is the magic behind facial recognition on your phone, helping you unlock your device with a glance. It also plays a vital role in security systems, identifying intruders and enhancing surveillance. Ever you said Google Translate? You can thank deep learning for its accuracy. Deep learning models analyze and translate text from one language to another, making communication across borders easier. Self-driving cars are no longer science fiction. Deep learning is at the heart of their ability to perceive the environment, make driving decisions, and keep passengers safe. These real-world applications showcase the incredible potential of deep learning and its impact on our daily lives. Having explored the depths of deep learning and its transformative impact, we now shift our focus to one of its most compelling applications, large language models, or LLMs. These models represent a pinnacle in our journey through AI, showcasing the remarkable abilities of machines in understanding and generating human language. Let's start by understanding what LLMs really are. These are not your ordinary language processing tools. They're like the giants of the language world. LLMs are built on a scale that allows them to grasp the intricacies and subtleties of human language. They're trained on massive text corpora, giving them a breadth of language understanding that's unprecedented. Imagine a model that has read more books, articles, and websites than any human could in their lifetime. That's the level of exposure we're talking about with LLMs. The evolution of LLMs, with models like GPT and BERT, has shifted the paradigm in natural language processing. These models don't just understand or translate text. They can write and converse, making them incredibly versatile tools in AI. Training LLMs is an exercise in both scale and technique. They're exposed to vast amounts of text, learning not just words, but the probability and context that govern language use. It's like teaching them the art of conversation and writing, not just the rules of grammar. Now let's move to the next concept, which is the architecture of LLMs, and it is a marvel in itself. At the heart of these models lies the transformer architecture, a breakthrough that has changed how we approach language processing in AI. Transformer models are a key reason why LLMs are so effective. They use self-attention mechanisms, which allow the models to weigh the importance of different words in a sentence, regardless of their distance from each other. This is a game changer because it means the context isn't lost in translation, so to speak. Training mechanisms like masked language modeling and next sentence prediction are what make these models truly understand language. They don't just learn words in isolation, they learn how words and ideas connect, flow, and relate to each other. Next is scalability and parameters. The sheer scale of modern LLMs is nothing short of remarkable. Take GPT-3, for example, with its hundreds of billions of parameters. What does this mean? Well, think of parameters as the model's knowledge base. The more parameters, the more nuanced and sophisticated the language processing. This massive scale allows LLMs to understand and generate text that's coherent and contextually relevant. When we talk about GPT-3's ability to write creative stories or answer complex questions, it's this scale that we're referring to. It's like having an incredibly vast encyclopedia that the model can reference to generate responses. The size and complexity of these models allow them to capture the intricacies and subtleties of human language, making interactions with them often indistinguishable from interacting with a human. Another remarkable aspect of LLMs is their adaptability. While they're initially trained on general data to understand language broadly, they can be fine-tuned for specific tasks and domains. This is where they become incredibly powerful tools for specialized applications. Let's say you have a legal firm that needs to analyze thousands of legal documents quickly. An LLM can be fine-tuned with legal texts, making it proficient in legal jargon and concepts. thereby transforming it into an efficient tool for legal analysis. Similarly, in the creative industry, an LLM can be fine-tuned with literary works, enabling it to assist in creative writing endeavors. This fine-tuning process involves training the model on a specific dataset after its initial, more general training. It's like giving the model a crash course in a particular subject area, equipping it with the knowledge and context needed to excel in that domain. Now, let's talk about where LLMs are making a real difference. The applications are as vast as they are impressive. In content creation, LLMs are not just assistants, they're creators. They're helping write articles, create poetry, and even draft scripts. It's like having an incredibly well-read and articulate collaborator by your side. Conversational AI has taken leaps with LLMs. Chatbots and virtual assistants powered by LLMs can now hold conversations that are more engaging, context-aware, and fluid. This is transforming customer service, making virtual interactions more human-like. Next is language translation, which has been revolutionized by LLMs. They're not just translating words, they're capturing nuances, idioms, and cultural contexts, making translations more accurate and natural. Information extraction and analysis by LLMs is another area where their impact is profound. They can sift through vast amounts of text, extract key information, summarize data, and even analyze sentiment. This capability is invaluable in areas like market research, legal analysis, and academic research. As we've seen in our exploration of large language models, the ability of AI to understand and generate human language is just the tip of the iceberg in the realm of AI's capabilities. Now, let's turn our attention to an even more fascinating aspect of AI, generative AI. This field is not just about understanding or processing information, it's about creating something new, something original. Generative AI is where AI begins to touch the realms of creativity and innovation. Think of generative AI as an artist with an infinite palette of ideas. It's a branch of AI where models are designed not just to analyze or classify data, but to generate new data instances, whether that's in the form of images, text, music, or any other type of content. At its core, generative AI learns from existing data to generate new instances that mirror the real world. It's like teaching a machine to paint. First, it learns from existing art, and then it starts creating its own. But how does it do this? It's all about capturing the essence of the data it's fed. Generative AI models learn the patterns, styles, and structures present in their training data. It's not just replication. It's about understanding the underlying principles and then applying them to create something new. The process of training these models involves exposing them to vast amounts of data. This exposure allows them to capture the complexity and variability of real-world examples. It's like giving them a world tour, showing them different cultures, styles, and expressions, and then asking them to create their own interpretations. One of the most captivating applications of generative AI lies in the realm of art and music. It's fascinating to witness AI systems creating paintings or composing music pieces that resonate with human emotions. These AI artists are powered by complex algorithms that learn styles and patterns from existing works and then generate entirely new creations. But generative AI's influence extends beyond the arts. In healthcare, it's being used to design new pharmaceuticals. AI algorithms can predict how different chemical compounds will react together, speeding up the drug discovery process. Additionally, generative AI plays a critical role in data science, particularly in generating synthetic data. This data is invaluable for training other AI models, especially in scenarios where real data is limited or sensitive. Another intriguing application is in product design. Generative AI can help design more efficient and innovative products by exploring a vast array of design alternatives, analyzing them, and suggesting optimal solutions. The benefits of generative AI are manifold. First, it automates and enhances creative processes. For instance, in graphic design, it can generate numerous design options, providing designers with a broader palette of ideas to choose from. Another key benefit is in enhancing data privacy. Generative AI can create synthetic datasets that mimic real data, allowing for the training of robust AI models without risking exposure of sensitive information. Moreover, generative AI is a boon in scenarios where traditional data is scarce. By generating synthetic data, it enables the application of AI in fields where data collection is challenging or ethically sensitive. However, with great power comes great responsibility. Managing the unpredictability of generated content is a significant challenge. There's always a risk of generative models producing inappropriate or unintended outputs, which necessitates careful oversight. Ethical use of generative technology is another critical consideration. Issues around authenticity and copyright emerge, especially when AI-generated content closely mimics human-created works. This raises fundamental questions about the nature of creativity and ownership. To appreciate the uniqueness of generative AI, let's contrast it with its counterpart, discriminative models. While generative AI is about creation, discriminative models are about distinction. Discriminative models are the more traditional form of AI that we're used to. They predict labels based on input data. Think of them as experts in differentiating and categorizing. For instance, they're used to identify whether an email is spam or not. The strength of discriminative models lies in their precision and efficiency. They're excellent at drawing boundaries, distinguishing one class of data from another. This makes them invaluable for tasks like classification and regression. Now, back to generative models. These models don't just categorize, they learn the structure of the data. They're not just recognizing patterns, they're learning how to replicate these patterns. This ability allows them to generate new data instances that are similar to, but distinct from, the training data. Comparing the two, while discriminative models excel in identifying and classifying data, generative models bring the power of creation. They provide a deeper understanding and a more versatile application of AI. The choice between using a generative or a discriminative model depends heavily on the task at hand and the nature of the data. But why choose? In many advanced AI systems, we see a synergy between the two. Generative models can be used to create training data for discriminative models, enhancing their learning and accuracy. This combination harnesses the strengths of both approaches. Building on our exploration of generative AI concepts in Module 7, where we delved into the fascinating world of AI's creative capabilities, let's now focus on the specific types of generative models that are driving this innovation. Understanding these models is crucial, as they are not only the engines behind the generation of new content, but also key players in advancing AI's frontiers. Let's discuss the types of generative models in AI. Generative models in AI are like the master artists of the digital world, each with its unique style and approach to creation. Among these, generative adversarial networks, GANs, and variational autoencoders, VAEs, stand out for their remarkable abilities. Let's start with GANs. Imagine a painter and a critic. The painter, or the generator, creates images, while the critic, or the discriminator, judges them. In a GAN, these two networks work in opposition, continually refining the output. The generator strives to create images so realistic that the discriminator can't tell them apart from actual images. This adversarial process leads to incredibly lifelike results, making GANs famous for their ability to generate photorealistic images. Now, on to VAEs. Think of VAEs as sculptors who mold and reshape data. They compress data into a lower dimensional, latent space, and then reconstruct it. This process of encoding and decoding not only helps in generating new data instances, but also gives us control over the generation process. VAEs are particularly effective in tasks where you need a balance between the quality of the generated content and computational efficiency. When choosing between GANs and VAEs, it's like choosing between different artistic techniques. GANs are known for their high-quality outputs, while VAEs offer a more structured approach to generation, often making them easier to train and manage. Next, we talk about the applications. The applications of GANs span from art creation to photorealistic image enhancement. They're also instrumental in data augmentation, where they generate new data samples to train other machine learning models. This capability is a game changer in fields where data is scarce or sensitive. VAEs find their use in areas like image denoising and anomaly detection, where understanding and manipulating the data distribution is key. Their ability to learn latent representations of data makes them suitable for complex tasks, from facial recognition to feature extraction in images. The evolution of generative models doesn't stop here. We're witnessing the emergence of new models that combine the strengths of GANs and VAEs, exploring innovative architectures for more efficient and diverse content generation. The field is continuously evolving, pushing the boundaries of what's possible in AI-driven content creation. Diving deeper into generative models requires a solid grasp of their theoretical foundations. This understanding not only helps us appreciate their capabilities, but also guides us in their application and further development. At their core, generative models are deeply rooted in mathematics, specifically in probability theory and statistics. They model the probability distribution of data, learning to understand and replicate the intricacies of this distribution. It's like learning the rules of a complex game. Once you understand the rules, you can play the game or, in this case, generate new data that follows these rules. Training these models, especially GANs, presents unique challenges like mode collapse, where the model starts generating a limited variety of outputs. Overcoming these challenges involves sophisticated optimization techniques and a deep understanding of the model's learning dynamics. The concept of latent space in models like VAEs is fascinating. Here, data is mapped to a lower dimensional space, capturing its essence. This latent space is the canvas on which VAEs draw, creating new content that is a variation of the original data. It's like a writer who captures the essence of an experience in a few poignant words. Evaluating generative models often goes beyond standard metrics. Since the quality and diversity of generated content are subjective, metrics like inception score and Fréchet inception distance are employed. These metrics attempt to quantify the perceptual quality of the generated images, a task that's as complex as judging art. The ethical aspects of generative models cannot be overstated. With their ability to create realistic images and videos, there's a potential for misuse, particularly in the creation of deep fakes. Ensuring the responsible use of these technologies is as important as their technical development. Looking forward, we see a future where generative models will become even more robust, diverse, and efficient. Their applications are expanding into more complex domains like 3D content generation and interactive media, opening up new possibilities for creativity and innovation in AI. Having delved into the various types of generative models in AI and their applications in our last module, we now step into the realm of their mathematical foundations. Understanding these underlying principles is crucial, as it not only deepens our comprehension but also empowers us to harness these models effectively. At the heart of generative AI lies the intricate world of probability and statistics. These aren't just abstract concepts. They are the tools that enable these models to learn from data and create something new. Consider probability as the language of uncertainty, a way to quantify the likelihood of different outcomes. In generative AI, this translates to understanding how likely certain patterns are to occur in the data. It's like looking at a complex puzzle and figuring out the odds of each piece fitting in a certain place. Now let's talk statistics. It helps us make sense of data distributions. By analyzing means, variances, and standard deviations, we gain insights into how data is spread out, which is crucial for training generative AI models. It's akin to understanding the terrain before embarking on a journey. Bayesian inference plays a key role here. It's a statistical method that incorporates prior knowledge into our models. Imagine having a hunch based on past experience and then updating that belief with new evidence. That's Bayesian inference at work in generative AI. Delving into random variables and distribution functions, we see how generative AI models mimic the real world. Different types of distributions, Gaussian, Poisson, and more, each tell a different story about the data. It's like understanding different genres in literature, each with its unique narrative style. Sampling methods are the techniques that allow us to draw conclusions from these complex distributions. Techniques like Monte Carlo sampling let us approximate these distributions, essentially giving us a way to predict and generate new data instances based on learned patterns. Lastly, estimation and hypothesis testing are the tools we use to refine our models. They are about testing our assumptions and fine-tuning our models to ensure they not only replicate, but also understand the underlying structure of the data. Moving beyond probability and statistics, let's explore the theoretical frameworks that form the backbone of generative AI models. Information theory is central in understanding how much information our models can capture. Concepts like entropy and information gain are crucial here. It's about quantifying the richness of the data our models can generate and understand. Machine learning algorithms are the foundation upon which generative AI models are built. Understanding these algorithms, their decision-making processes, and how they learn from data is fundamental in developing effective generative models. The architecture of deep learning models, especially in generative AI, is rooted in complex mathematical and computational principles. Understanding how convolution works, what pooling layers do, and how neural networks function is key to grasping how these models generate new data. Now we'll discuss more about the theoretical framework of generative AI models. Here, optimization is a critical aspect of training generative AI models. It involves finding the best set of parameters for our models. Concepts like gradient descent and backpropagation are not just technical terms. They are the gears that drive the learning process in these models. Then, regularization techniques are our safeguards against overfitting. They ensure that our models are not just memorizing the training data, but are learning to generalize. Techniques like dropout and L1-L2 regularization are essential in maintaining the balance between learning and overfitting. Understanding the theoretical limits and trade-offs in generative AI is about recognizing the balance between precision and creative freedom. It's about knowing the boundaries within which these models operate and how we can push these boundaries to explore new possibilities in AI. As we weave through the mathematical tapestry that underpins generative AI, we gain not just technical knowledge, but also a deeper appreciation of how these models function. As we reflect on the expansive landscape of artificial intelligence that we've traversed together, let's succinctly recap the core insights that have shaped our understanding of this transformative field. We commenced with the fundamentals of artificial intelligence, where we acknowledged AI as the embodiment of systems striving to emulate human intellect and its propensity for learning, reasoning, and adapting. Progressing to the basics of machine learning, we recognized it as the lifeblood of AI, a discipline where computers are not just programmed, but nurtured to learn and evolve through data and iterative experience, much like humans do. Our introduction to neural networks illuminated the complex mechanisms that are the cornerstone of AI's perception and decision-making processes. These intricate algorithms, akin to a human brain's web of synapses, underscore our journey into recognizing patterns and relationships within vast data troves. With the deep learning overview, we dove deeper into the ocean of AI. Here, neural networks form the bedrock of systems that learn representations through multiple layers of abstraction, transforming raw input into discernible concepts and reasoning. The segment on large language models marked our foray into the domain where AI wields the power of language. These sophisticated models, trained on extensive corpuses of text, stand as testament to AI's burgeoning capability to process and recreate complex language constructs. Our exploration of generative AI concepts led us to the frontier where AI transcends conventional boundaries, learning from existing data not just to analyze, but to create, to generate new instances that mirror the learned patterns with uncanny resemblance. Discussing generative models in AI, we ventured into the realm of GANs and VAEs, algorithms that are the engines of innovation, driving AI's foray into the creation of data instances that are unique yet reflective of their originating data sets. And finally, we cemented our journey with the mathematical foundations of generative AI, the bedrock upon which the edifice of generative AI is built. Here, statistical and probabilistic theories intertwine to empower models to generate data that faithfully echo the complex patterns of their training set.